Hi, my name is Sanat, and this is our work on multi-agent reinforcement learning, in collaboration with my partner, Veerpong. We're both students of the University of Texas Computer Science Master's Program. A lot of novel algorithms like Sarsa Lambda, deep Q learning, have come out of single-agent scenario research, and most of the research in reinforcement learning has focused on single-agent scenarios. However, a lot of scenarios in games are inherently multiplayer and multi-agent. An example of this in class was robot soccer, where every single robot has to collaborate on a particular team, has to collaborate in order to achieve their ultimate goal. This prompted us to research this particular topic. We used OpenAI's multi-agent environment and specifically focused on predator-prey scenarios, or as we call them, adversary-prey scenarios, with the goal of promoting cooperation between the adversary agents. We have three adversaries and one prey, similar to the image we use. Every adversary gets a positive 10 reward every time a single adversary collides with the prey. Similarly, prey gets negative 10 reward every time it gets collided by an adversary, or if it goes out of bounds. Our action space is 5 dimensions and our state space is 16. In order to facilitate this, we use three different algorithms. We use Sarsa Lambda, we use deep deterministic policy gradient, and multi-agent deep deterministic policy gradient.
We first look at Salsa Lambda because Salsa Lambda is a long has been a long well understood traditional RL algorithm. In particular, in our implementation, we use the true online Salsa Lambda that's provided by Rich Sutton, and we also learned this in class extensively. And we use it in a combination of tile coding as well. And the main reason we picked that is because the promising result that we've seen in Keep Away Soccer shown by Professor Stone. So next algorithm is DDPG. So essentially DDPG is a policy gradient algorithm. Uh, it uses actor critic algorithm, and it is a model free learning algorithm, and it's also off learning, right? One of the main one of the main tweak that made DDPG very successful is that it leverages neural networks in its implementation. So uh, in our implementation, it has two networks, one for actor and one for critics. So the last algorithm that we looked at is MAD-DDPG, which is also an extension on top of DDPG. In this case, MAD-DDPG takes into account policies of other agents during learning. So you can think of it as is there are multiple actors but only one critic.
So this is Sarsa Lambda at episode 100. As you can see, they were able to hit the green, so they got a reward for it. And this is Sarsa Lambda at episode 28,000. In general, Sarsa Lambda did not work well. The average reward, in fact, went down over time. And we ascribe this to the fact that in order to make it computationally tractable, we had to reduce our state space from 16 all the way to 5, and we believe we might have added a lot of noise in garbage data when we reduced the state space so much, which led to inefficient learning. We next looked at DDPG, which we had a lot more faith in, since it uses neural networks to reduce the state space more efficiently. DDPG at episode 13,000, and we trained it up till episode 5,000. Surprisingly, DDPG does better, however not as good as we thought it would do, and we were a bit confused as to why. And we tried a single agent DDPG network, and it turned out to do extremely well. It turned out to do so well, in fact, that the adversary reward was close to 100, and the average reward, which we expected to be 0, because the agent reward, the adversary and the green agent's praise reward should cancel out, it was actually -5 plus because the adversary was so good it dragged the prey outside the board, thus resulting in negative rewards. Mad DDPG, on the other hand, ended up doing pretty well. By episode 15,000, the agents had started working together, and by episode 25,000, they were working as a cohesive team and really narrowing the prey. So you can see the average reward increased linearly almost um, as the episodes passed by, and so did the adversary reward. So Mad DDPG blew all the competition out of the water because it was able to leverage a single critic and utilize other agents' action space as well as their current state while figuring out the Q values for each particular agent. In conclusion, we found that traditional reinforcement learning techniques often don't work well in multi-agent settings, which is why having specialized algorithms such as MAD-DDPG or MAD-DPG helps in those particular scenarios. Secondly, we found that neural nets were much better at approximating uh, than tile coding, and they were much more computationally efficient as the number of dimensions increased. Thank you so much, and thanks for a great semester.